Okay. Ooh. Welcome to this year's edition of the workshop on higher order programming with effects. Let's get it right started with Paulette, who will be talking to us about Landin's knot.
Hello. Okay. I guess the lapel mic works pretty well. Oh.
Okay.
Oh, we're playing the stream while we're doing this. That's awesome. Okay. Yeah.
Where's the ghost, Max? All right, are we good to go?
Yes.
Cool. All right, so thank you all for coming to my clickbait title talk. I'm actually going to talk about, instead, how to get William to wear a giant bow sometime during this week. So thank you for attending that. No, just kidding. So this is joint work with William, and we want to thank Amazon Research for funding this line of work. So to wake us all up, I want to start with a question for all of you here. So I'm expecting audience participation at this point. So given a functional, strongly typed language, think SCLC, when we add higher order references to a language like SCLC, is it still terminating? So there's no tricks here, no linear types, just think SCLC.
No.
Yeah, so a lot of you are saying no, thank you. So let's go into why this is. So the reason why a language like SCLC, when we add higher order references to it, is no longer terminating is an idea commonly referred to as Landin's knot. So the general idea behind Landin's knot is we kind of capture a mutable reference in a function's environment and later update this reference to contain itself. So we can see this through a pretty small example. So this example, I'm going to start off by just defining the identity function on natural numbers. This isn't very interesting, but I want to have an initial value for this mutable reference that contains a function from naturals to naturals. So I'm going to go ahead and initialize this reference R with the initial value ID. Now that I have this reference R, I'm going to refer to it in a different function f. So what f is going to do is it's going to dereference this reference R, whatever function happens to be in it, and it's going to apply it to its formal parameter n. So this function f is a function from nat to nat, so it's perfectly well typed to update the reference R to contain the function f. And finally, when we try to apply this function on some natural number, well, we'll go into the body of f, we'll dereference whatever function is in R and apply it to the same argument, which we find to be f, because we just updated this reference to contain f itself, and so we find this cycle. I could keep going for 20 minutes, but I think you want to hear about other things. So let's take a look at this example sort of in more detail. And in particular, I want to draw your attention to this reference R, which is in the function f's environment. So originally, when we defined f, we're referring to the identity function. So if we were to call f at this point, we'd get a fine terminating program, as we might expect in SCLC. Of course, this isn't actually what happens. What happens is we end up updating this reference to contain f itself. So really what's happening is that the recursion that we see come up is not due to the fact that we can hold functions in a reference, but it's due to the fact that we can now update the function f's environment, which isn't an ability we had with SCLC originally. Okay, so given that we have made this observation that this is an update to the function's environment, let's try to make a function environment explicit so that we can kind of study that more deeply and also think about the types going on here. Okay, so if you want to make a function typed environment explicit, what we typically encode functions as then is as closed code along with their explicit environment. The reason why we close the code is we want to make sure that there's no implicit environment still around. What environment we pair it with is the one that it's for sure has. So we want to study this function f, so I've copied it here again. So clearly this function f is not closed. It has this free reference R. So to close it, we add an extra parameter to represent R. We'll just call it env-r here, and then we're going to pair it with the value of R. And to make this a little bit more general, we generally have just one environment parameter, which is a tuple of all the free variables that our function has, and then we'll just project out all the free variables we need. In this case, it's just one, so we're just going to have a tuple with a single reference R in it. Now this final pair here at the bottom is what we refer to as a closure, and we've can see the closures explicitly here, but let's now think about the types of closures. So we typically type closures using existential types, which have the following form. There's this type variable alpha, and it also includes another type A in which this type variable alpha can appear. So then how we represent closures is if we have a function from A to B, we have this existential type to represent it, where the type variable alpha is going to represent the type of the environment. And you kind of see this show up in the rest of the pair type, where we have the close code that takes an environment as an argument, and we also pair it up with a value of the environment. Now notice there's no details about the environment here. It's just the type variable alpha. It's completely abstract. We don't know what types are in the environment. We don't know how long it is. All we can do with it is pass it to this closed code. So to come back to our concrete example of our closure and see how these types line up, we see that we have this extra environment parameter highlighted in blue, and then we see the value of the environment highlighted in kind of a reddish pink here. Finally, we need to actually instantiate this type variable with a concrete type. So we use this pack form along with the type and the type in which we're instantiating the type variable alpha. And here in orange, it's going to be a tuple type containing a reference. OK, so we went on this whole digression to kind of revisit our example of Landin's knot explicitly with environments. So let's go back to that. So there's a lot of things on the slide here. What I really just want to draw your attention to is we have now, instead of two functions, we have two closures. And these two closures, ID and F, have two different environments, highlighted in pink here. But despite these differences, they actually end up having the same type, because we've abstracted over the type of the environment. We don't know any details about the types. And in particular, it's the same type that this reference R is expecting. OK, but we knew there was something special going on with F and its environment. So let's kind of unpack it and see what type we're instantiating for the environment. So the type that we're instantiating for the environment is going to be a tuple type containing a reference. Inside of that reference, and highlighted in magenta, we see that it happens to be the exact same existential type that is typing F here. So that is, this type variable alpha is going to be instantiated with the same type it finds itself in. This is what we refer to as impredicativity, when a type variable can be instantiated with what it's quantifying over. And so what we find by closure converting this example is that later, when we update the reference R to contain the function F, inside of this reference, we also instantiate the type variable with the same type it finds itself in. So the update to this function's environment is actually well typed due to impredicativity, the fact that this type variable alpha can be instantiated with itself. OK, so let's quickly recap what we've seen so far. So by studying Landin's knot in detail, and in particular thinking about functions environment, we found that this non-termination or recursion is coming from an update to the function's environment, a capability we didn't have before in SDLC. And by closure converting the example and seeing the types of the environment explicitly, we get to see that this is well typed due to impredicativity. OK, so given this last insight, that this update to the function's environment is well typed due to impredicativity, an idea then is, can we actually rule out non-termination or Landin's knot using predicativity instead? So let's take a look at that. So if we wanted to add predicativity to our type system, we would add this type level system and some annotations on our existential type. In particular, we would annotate the existential type here with the highest level of a type for alpha. Then the existential type itself is kinded at a level higher than what alpha is quantifying over here. So, and we're using these double colons to represent kinding here. So clearly this prevents self-reference because alpha has to be at type level I, but we have our existential type be at type level I+1. It's not really a way to make those numbers line up. Hopefully not. But we find that while this could rule out Landin's knot or non-termination, it rules out a little bit too much. So in particular, it rules out higher order functions, and we would like to have those. So let's digress and see why that is. So here we have a function. I hope you're not tired of functions yet, right? This is ICFP after all. So here we have a function g, and inside of g we call some other function f. And we're going to say g is a nat-to-nat function, so clearly f has to have type nat-to-nat. So recall that the type translation for converting to closures is going to look like this, where we're going to get, for a nat-to-nat function, we're going to get the following existential type. So since g has this free variable f here, we're going to have to, when we convert it to a closure, include f's type when we instantiate alpha. But it turns out f's type is also exactly g's type. Even though they're not the same function, they have the same type. And so we find that in g's environment, we're actually quanting over the same type that that alpha finds itself in. So we still need this impredicativity. OK, so we're a little stuck. We need impredicativity for higher order functions, but we need some sort of predicativity restriction to rule out Landin's not. So if we think a little bit further about what we really want to prevent in our functions, is we want to actually prevent the ability to have mutable self-reference. And this kind of relates back to our idea that this recursion is due to the update to the functions environment. So we don't want to prevent any self-reference, but in particular mutable self-reference. And so this leads us to define instead a predicativity restriction on references. So let's take a look at what that would look like. So here at the top I have the rule for references, where we're going to raise the type level of a reference based on whatever type it stores. So here we have the type variable a, or the type a at type level, kinded at type level I, and so a reference storing a is going to be at type level I plus 1. Note here, though, that we'll still have our existentials be impredicative so that we can encode higher order functions. So here we have the kinding rule for existentials. We're still going to annotate alpha here. It's going to be annotated at some type j, but the existential is going to be at type level k, and there's no restriction between j and k here. They could be the same. One could be bigger, one could be smaller. OK, and then for actually annotating the type for an existential, we just check whatever witness type we have here, tau. We just check its type level and then annotate alpha with that type level. So we just add an extra premise to our existential typing rule. OK, so coming back to our example, so given with our predicative references and annotating our existential types, we'll have the ID closure here, and highlighted in blue we have its environment. There's a lot of dots in between, but I just want to actually explicitly see the environment here. So the environment for the identity function is just going to be empty, so it's basically the unit type. And so the type annotation we have on alpha here is just type 0, just the base type. Here we're going to have the reference r's type, and it's the kinding of that type. So since it's a reference, and it contains something at type level 0, a type, then it itself is going to be kinded at type 1. Some dots later, and here we're going to have f's and f's type. So f's environment is a tuple containing r, and we have the annotation actually end up being type level 1. This is because f's environment contains a reference r, and we can see the kinding here is type level 1, so f's environment has to be a type level 1. So we find that actually when we try to update the reference r to contain f, it's no longer well typed because the environment types of ID and f differ. So initially we initialize r with ID, so it's expecting functions with environment type level 0, but f's environment is of a higher level, so we can no longer do this update. OK, so it seems like we have some sort of restriction that could rule out Landin's not. What's sort of next? Well, we went on this little adventure to see closures and see environments explicitly. That led us to adding this predicative ref rule, but keeping our existentials impredicative. But it turns out not everyone likes programming with closures. So ideally, we would like to kind of back translate these restrictions to a source language in which we can kind of program with the usual function type. The problem is that this impredicativity that we kind of see more explicitly using existential types is actually hidden in the function type. If you think about function nat to nat, all you're reasoning about is the input and output types. You know nothing about the environment. So let's take a look at how we encode this. So up on the slide again, I have the typing rule for existentials, that is typing rule for closures. So equivalently in a source language, we'd have the typing rule for functions. And then highlighted in blue, we have the extra premise that we need to get the type level of the environment. So equivalently in the source, we actually need to get the type levels of the free variables in the function's body. This is what makes up the function's environment. So what we end up with is a very funky type and kinding rule. It looks like this. It's very explicit. Ideally, we'd remove some annotations, but for now, I just want to keep everything explicit. So here, the kind of a function type isn't reliant on the input or output types A or B, but it's completely reliant on the maximum type level of the free variables, here being type max, just to emphasize that, so type max. Okay, so given a source language with this really funky type and kinding rule and predicative references and higher order references, is it finally terminating? Have we figured it out? We don't actually know. Well, we have some intuition that it might be. So let's go into that intuition that we have. So we'd like to prove that this language is terminating by modeling it in a different language. And in particular, it's going to be a language with a store. So this store is going to represent those mutable references. It's going to be mapping the locations to their values and update them as they change. So typically when we model languages with references, we end up modeling function types as store passing functions. So the idea is that a function can execute in any kind of store and return a possibly new updated store. Now we find with our predicative ref rule that we actually end up stratifying the store. So if you think back to the typing rule, all the references store types one level lower than them. So a store at level I+1 is going to be mapping locations to types at level I. So then the idea behind our proof then is, well, we can equate store level 0 to be roughly equivalent to a ground store, that is a store that only stores base types, which we know to be terminating, and then we can proceed by induction on these store levels. So to see this a little bit more visually, we have this stratified store, and locations in store I+1 are pointing to types that can be typed at store level I. There's no cyclic dependencies here, so locations in store I+1 aren't going to be mapping back to types at store level I+1. And so then the idea of our proof is, well, store level 0 can be a ground store to be terminating, and then by induction on these levels, we can prove the whole language terminating. So let's think about what's in our store level 0 here. So there's no restrictions on what references can store. We can still store functions in references, but at store level 0, they're very particular functions. They're functions that we know have no references in their environment. So given this fact, is store 0 actually terminating? We don't know this for sure, but we have, again, more intuition as to why it might be. So let's go into that. So the intuition we have is that we find that actually a language with closed functions, and what I call closed order references, that is references that only store closed functions, actually turns out to be terminating. So we can convert it to a language with a ground store, which we know to be terminating. And so the relation to our store 0 proof is the idea that store 0 here is going to be closed with respect to references. And so this closed order reference proof might come in handy for showing that store 0 is terminating. Okay, so let's go into the proof for closed functions and these closed order references. So the proof for this closed function language proceeds by defunctionalization. So usually defunctionalization is used to convert higher order functions to first order functions. Here we're using it to convert closed functions to base type data. So as a concrete example, I have two closed functions here. I'm just going to convert the first one to 1 and the second one to 2. But you might be thinking, how is this possible? We had all this trouble of encoding functions before. Well, the key here is we no longer have to care about the environment So all the work we did to preserve the environment and type it, we no longer have to worry because all these functions are closed, so we don't have to worry about the environment at all. But you still might be wondering, these are functions, how do we now apply numbers? Well, the idea is that these numbers are now kind of like labels. And so we kind of pattern match on the label and decide, if it's 1, we're going to just do the first function's operation, and if it's 2, we're going to do the second function's operation. Okay, so to see this play out a little bit in the types, when we convert our closed function reference types, we kind of convert them as you might usually see it. But what's really changes is we actually end up converting function types to finite types n, where n is the number of functions with that particular type, a to b. And you can see that clearly there's no more functions and references because there's no more functions at all in this language. And so we converted it to a terminating language with a ground store. And big thank you to our session chair, Max, for this insight and proof. Okay, so given all this information, is our language actually terminating? This is still work in progress, but the intuition is that we'll proceed by induction on these store levels, and that we can roughly equate store 0 to be a ground store, maybe through some sort of neat defunctionalization trick as well. Okay, just to sum up, so we took a long look at Landin's knot and found some observations. In particular, we found that the recursion that appears in Landin's knot is due to updating the function's environment, and updating the function's environment is well typed due to impredicativity. So this led us down the path of, well, can we have some sort of predicativity restriction to rule out Landin's knot? And we found that we wanted a predicativity restriction on references. And this led to a stratified store, you see here visually. And the idea then of our language being terminating is that the store is just relying on this smaller stratified store. Thank you all very much.
Great, thanks, Paulette. Sam's got a question.
Should I take the mic?
Yeah, that would be helpful. Thank you.
This is very nice. It reminds me of some confusion I had, about 10 years ago, when we were trying to work out a calculus for effect handlers. And at some point, I was convinced that it couldn't be terminated, because I thought we could encode Landin's knot. But actually, we can't. So the point there is that you have an effect type system that keeps track of all of the operations you're allowed to perform. You can store, so it's very easy to implement state. You can store higher order functions, but if you try to write Landin's knot, then you actually end up needing a recursive effect type.
Right, yeah, exactly.
And it's simply not possible. So there's a very similar kind of stratification going on there. I don't know if you've considered the relationship between effect type systems and what you're doing.
I'm not sure what's wrong with that mic.
Oh, is this not really?
In fact,
It's gone off. Is it working now?
Oh, that might be
tree,
that.
Yeah,
to traverse
it's
it.
Okay.
You traverse every tree.
Oh, fun. We're 2 sessions at once. I love it.
Check, 1, 2. All right.
Okay.
Did any of what I said come
Yeah, I mean, well, I heard it, but others.
Is this on?
This is on. Yes, this is working.
Okay, I'll say that again then. So I was referring to my confusion when I was working with effect type systems for a handler calculus, and I expected that to be non-terminating because it seemed like we could encode higher order state, but actually in order to do that you needed the effect type to be recursive, and it couldn't be. And we were able to prove that it actually was terminating. And I was wondering if you've considered the relationship between what you're doing and effect type systems. It kind of looks like you have a kind of effect type system anyway, that the constraint is on the body of the lambda. That's the thing you're propagating.
Yes, definitely, yeah. Yeah, we'll be at the Shonen meeting for effect handlers, so that will be great to have people tell me. And yeah, I would love to talk about it. But yeah, we just also noticed that, yeah, in order to encode Landin's knot, you need some sort of recursive type, or these impredicative types if you're in a closure-converted language. So yeah, I would love to talk about the relationship between effect systems.
Hi. So it seems like there's a fairly obvious sort of way forward in the proof that you sort of keep doing the defunctionalization argument. I mean, this is like my thought after having sat here for a minute. So I'm sure things go horribly wrong. I'm just curious, can you give a sort of a brief idea of where that breaks down?
Yeah, well, I think it should be relatively straightforward. The idea then is just that we need to prove that indeed these functions in store 0 are closed with respect to references, so we can kind of encode. I can imagine that we'd probably, instead of using defunctionalization, we still need to encode the environment in some way, but we know this environment doesn't have any references in it, so we can kind of not worry about that, it'll be updated. And so I think the difficulty is just figuring out how to encode that environment and prove that there's, nothing bad will happen, basically.
I have a question.
Oh, prime seat.
I thought the student volunteers were supposed to be running around now.
I'm trying to think about what kind of classes of programs this would exclude. For example, would you be able to implement an interpreter of this language in itself?
Yeah, that's a good question. I'd love to think about it. I haven't thought that hard about the classes of functions. Really, we're trying to restrict it to the terminating functions. So if there's a terminating way to do that, then probably, but...
Yeah, it seems a little tricky because if this proof is correct, or if you manage to prove that everything should terminate, then the interpreter should terminate too. But I don't know, if you have a self-interpreter, maybe a little weird. Thanks.
Okay, I have a less specific version of the same question, which is, you added this impredicativity restriction for references, right? And that's going to rule out some programs that were previously well-typed. You get something in return, but do you have any idea of what kind of programming patterns are ruled out by this kind of system? Besides Landin's not?
Yeah, I mean, I could imagine there might be some cyclic data structures maybe that it can work out with. That would definitely be an interesting case study to figure out what exactly. There's actually some useful programs that people want that end up being ruled out.
Benign programs.
Yeah, exactly. So, but I'm not entirely sure.
Any other questions? Okay, let's thank Paulette.